fluids exerted pressure. We talked about how liquids flow, and there's no flowing gas. Is there? There's flowing gas, sort of. But yeah, when we can compress it, right? We talked about kinetic energy and how we can add kinetic energy to different states of matter, how that changes it, how that will speed up the, when you add, it's adding heat, right? When you add kinetic energy, we can change the state of matter and how that increases the intermolecular attraction. Wait, did I just say that wrong? I just said that wrong, didn't I? No, I didn't say it wrong? Okay, good. Okay, did I just say that wrong? No. How solids have very high intermolecular attraction because their molecules are in fixed positions, and but they don't have other things, right? They don't have any flow. What else don't solids have? They don't take the shape of their container. They don't have cohesive forces. Yep, good. So we looked at all the different characteristics of each of the states of matter. Then we also talked about something called latent heat. And what was latent heat?
I forgot.
Energy needed to change state.
Very good. The energy needed to change the state of matter. Very good. What's the matter?
I was listening with my calf and then it like flung out my face and it scared me.
You're awake now. Okay, all right, so something new that we're going to talk about. We're going to talk about density. We're going to talk about, here he is, Mr. Avogadro, also lovingly known as Avocado. Alejandro. That's new, I like that one too. And something called specific gravity, and then how it applies to respiratory therapy. And we talk about specific gravity. We're talking, it's okay, we're gonna measure that with a hydrometer. Something we probably haven't learned about yet, hydrometer, okay? So we're going to be looking at density. Now I don't want you to get scared when we talk about density. Can I erase this?
Let me take a picture.
Oh, okay.
Sorry. Extra information. Take a
Can I-
picture. Because the sophomores told me to write down every single equation that we use from the beginning till now. They said,
Don't give it to them.
I gotta write them all down.
But they should know this anyway. They better know this. I should pop quiz them on this. Wouldn't that be fun?
No, don't scare
Extra
them.
credit.
Don't scare them.
No.
Jose said you like to throw stuff in there from like a long, long time ago, and he'll be like, "What? What is this?"
They should know it. We should all know it. Anything is fair game. Okay, all right, so when we talk about density, we're just talking about mass over volume. Okay, like in its simplest form, mass over volume, all right? And how pressure affects that, how temperature affects that, and so it's not like density seems odd, like how do we even define that, right? But that is the simplest way we can define density. Okay, our next slide has some different terminology on it. Some may be new to us, and some may not. So mass and weight and density, I think, get confused a lot, and they tend to be used interchangeably, but they really are separate things. So mass is the amount of matter. So the amount of matter that an object actually contains is an object's mass. Versus weight is actually the effect of gravity on something. So the effect of the pull of gravity an object has on something. So, which is, I think, a lovely to think about, right? So it's really not our fault how much we weigh. It's the gravity. It's the pull of gravity on us. Which, I mean, so we can really just say that, right? Like the scale is wrong. Like it's not. It's the effect of the gravitational forces on the earth about how much I weigh. All right. So, right? That's fine. I don't care. It's just a number anyway. So next time you get weighed at a doctor's office, you just tell them that. the effect of gravity.
They were like, okay, well, you may want to
I'm like, you want to write that down, fine, okay? And I always tell them take off 5 pounds from my clothes, okay? And my shoes. That's it.
Becky's
Right?
like, well, I should take my shoes
And they always say that's fine.
They're like, it doesn't matter. You take your shoes off. No, I'm going
It's
to.
fine because I wear myself totally naked at home, so.
I know what I really
I
like.
know my jewelry, all my jewelry, and my clothes and my shoes weigh at least 5 pounds. So that's 5 pounds. You write that down. And gravity. Gravity today has more pull on me than it did yesterday. All right. So that's all in your notes. Probably extra credit on the next test. Okay.
Okay.
There it is. All right. So it's different than mass. Okay. And then here's your density, right? Mass over unit of volume. So that's density. Okay. So when you say something's dense, right? It's just talking about, it does not mean that they're not smart either. Okay. Don't say that. I'm not gonna go there. Okay. Versus something called specific gravity. So this is actually a comparison. And this is something that we actually do use in medicine. So when we're comparing the density of a substance to the density of a known standard. So a lot of times we will use this in particular when we're looking at the specific gravity of urine, which sounds like, why in the world would we need to know about the specific gravity of urine? Weird, right? Actually, it's not weird. I probably, she's like, I don't know, Dr. Gardner. No, seriously. Okay, so when we're looking at if somebody has like a UTI, right? Or if somebody has, if they're spilling ketones, sugar, right? Other substances into their urine, it's gonna make the specific gravity of their urine different, right? It's gonna make it actually heavier because those things fall out of their urine, right? So we're gonna look at that in comparison to a known, which is water, right? So we're gonna be comparing that to the density of a known standard of water and then looking at the comparison of the density of their urine, okay? So if they have something that shouldn't be there, right, it's gonna make that specific gravity heavier versus what we're comparing it to, okay, that known standard. So that's how we use this in medicine, and we do it for other substances as well. And if we go to the next slide, I'm sorry, she's over there like trying to take notes. So when we look at densities of solids, we can look at densities of liquids, or density of gases. So that is also where we want to look at how dense are the gases that we give to our patients. For example, how dense is medical air versus how dense is oxygen, how dense is helium, right? So we're talking about dense, right? Again, it is mass over volume, but we think about that as in like really how lightweight, right? How lightweight, how fast is this air or this gas or this helium going to travel through the airway? And that becomes important when somebody has very high work of breathing or they have a very narrowed airway. Okay, in particular, like an asthmatic. So when the airway is very narrow, the radius becomes very small. Even the lightest weight gas cannot travel readily through the airway. So we have to use a very low density gas like heliox, okay? And we're gonna use helium to be almost a carrier gas for our oxygen. And that's why it actually works, because of its low density. And so we're going to be actually using an equation.
Sure.
There's just one more. To calculate the density, don't you shake your head. To calculate, it's very easy. It's a really easy one. To calculate how dense that gas is, so we know how quickly it's going to travel in the airway, okay? So it actually really is important to us as respiratory therapists, so that we can determine that, and then we know which gas to actually provide to the patient. And it is all going to come back to another gas law. Oh. And you probably have heard me talk about this one. Poisson? Anyone? Poisson? Anyone?
With the P?
Yeah. Poisson.
The one we learned again earlier.
Yes, you've already learned this one, right? We talk about how when the radius, Poisson, he was French, very fancy, Poisson. It's really hard to spell. Which he talked about how when the radius of an airway is reduced by half, right? Then the flow moving through the airway is changes by how much time? 16-fold. That's right, 16-fold, right? So that's huge, right? That's huge. And that means that for us, then we have to increase our driving pressure 16 times. So if we're mechanically ventilating that patient, we have to increase our driving pressure 16 times. Well, we really don't want to do that, okay? So there are other things that we want to try first, like providing a low density gas, right, to push through those areas. And then we're going to look at flow patterns in the airway too. And you may have already seen or heard some of these terms: laminar, turbulent, right? And then what?
It's a third one.
There is a third one.
Tracheal,
bronchial.
It's a mix.
And there's mixed pattern too, yes. And every point in the airway where there is a bending or a change of direction, then that changes. Okay, all right, let's take a look at what we got. Okay, so density. Density can be expressed in several ways because we have a mass and then we have a volume. Okay, so mass, again, is expressed as a weight, okay? Because if you go back to our definitions, what did it say? The amount of matter an object contains, right? So it's expressed as a weight. And so it can be expressed as pounds, it can be expressed as grams, it can be expressed as milligrams, it can be expressed as kilograms. Okay, so you're gonna see a weight measurement up here. And then your volume is expressed in, now this is kind of where it gets a little silly, cubic inches, cubic feet, milliliters, or liters. Generally, it's going to be expressed for you in mils or in liters. Okay, so primarily you're going to see this in grams per liter. Okay, that's what we're going to usually use for our purposes. It's going to be grams per liter or, okay, grams per milliliter. And I'm going to tell you why. Because when we're talking about solids and liquids, that's going to be grams per mil. So solids, liquids are going to go here. And then we're talking about gases. That is our gases. That is our grams per liter. Okay, because remember that gases can be condensed. So we can fit a lot of gas right into a very small container, which is why we use liters up there, because you can fit a lot into a small amount. So you're going to have a lot more gas than you are solids or liquids, which is why we talk about mils in that arena. All right. Okay. Our next slide, we're going to be looking at what does that actually look like. So we've got grams per liter and then 10 grams per liter over there. So 20 grams per liter just looks like your molecules are a little bit larger versus 10 grams per liter. We're occupying the same space. As you can see, the container is the same size, and so actually just the molecules look a little bit larger. There is a med calc, I think, on the next slide. So if you view this at home, and you just click on the hyperlink, you've got a density lab, like a little calculator thing. You can go there. It's kind of cool. You can see the things. You can see that container thing change and the molecules change size. So it's kind of fun to see that in action. Okay, let's look at how density actually, how temperature affects density. So temperature, hot or cold, right, is going to affect density because we're talking about the expansion and contraction of that volume. It's going to have the biggest impact. Temperature has the biggest impact on density, which kind of makes sense because we're talking about kinetic energy, right? So that's what temperature plays a role in here, is that kinetic energy piece. So we're talking, this is where our standards come in, right? Why you have to know those standards. So at STPD, so what's the STPD? Standard temperature, pressure, dry, pressure, dry. Okay, so we're at 0 degrees Celsius, we're at 1 atmosphere, and we're under dry conditions. Okay, so we're talking about STPD, the density of water is 1 gram per milliliter. That's a standard condition. So this is gonna be important, you're gonna wanna highlight this, because this is actually what we are comparing things to. STPD, the density of water, is 1 gram per milliliter. You're gonna want to know that.
And that's like no matter what.
No
That's
matter what, that's a
Okay.
standard condition.
Okay.
It does not change.
not per like
Nope.
each question.
Nope.
It's per that.
Nope, it will not change. You're going to be using that to compare things to. Okay. Oh no. No, didn't need it. Were you recording though? You were recording? Oh no. It's right here, over here. I was like, I didn't think you were texting.
Thank you.
I was like, if you were.
No, I got it. It's all new information.
Yeah. Okay, let's look at the, let's talk about density of gases next. All right, okay, now, much like when we were talking in the previous lecture about gases and how they were affected the most by changes in temperature, they're all, well, actually I just said that, right? Gases are greatly affected. If I would just look at my slide, right? I just said it. Gases are greatly affected by temperature and pressure. Of course they are. Okay, here's another standard that we need to sort of highlight and understand, because this is going to lead us into Alejandro. Okay. So the density of gas, and now we're going to be looking at something called gram molecular weight. That's what the GMW, not BMW, GMW. All right, gram molecular weight. So we have, oh, it's really being a stinker, isn't it? You almost need like a holder up there. Some Play-Doh, something. Okay, so our density of gas, at gram molecular weight is 22.4 liters. So this is another standard that you do need to know, and I'm going to talk about why and how all that works together, okay? And again, this is based off of Avogadro's law, all right? So let's look at what that means. So what is Avogadro's law and what does it say? And I hope that's not what he looked like, because that's scary, right? And his name was Amadeo, right? Is that where that song came from? Or was that, do I have that right? Amadeus, it was Amadeus, but I don't know, whatever. Okay, so what did he say? So he said a very long time ago, equal volumes of all gases. So this is true for all gases, doesn't matter what kind of gas it is. Equal volumes of all gases at the same temperature. So here's our standards. Our same temperature and the same pressure contain the same number of molecules. Okay, so this is where it gets a little bit dicey, so just stay with me, okay? So it doesn't matter what the gas is, but if it's at the same temperature and the same pressure, so we gotta kind of put that in our head, has the same number of molecules. All right.
Same temp, same pressure equals same
Yes,
number of molecules.
yes, okay. So I'm gonna sort of try to compare, write this down for us. Okay, so if I have, let's say I've got nitrogen in here, I've got oxygen in here, and let's say I've got helium in here, okay? The temp, 0 degrees. I just picked the temp, bitter. Okay, the pressure, 760. Oops. Okay, so I've got same temp, I've got 3 very different gases. nitrogen, oxygen, helium. Very different. And if you looked on your chemical, your periodic table, who can envision that? So lovely. I can. But y'all know I'm a nerd, right? So that doesn't mean anything, right?
I might not know all like
Right,
the
they're
sections
very-
but I can see it.
Very different densities of gases, okay? Even if you don't know your densities yet, you can probably at least gather that, right? Okay. But they're all at the same temperature, and they're all at the same pressure, which means that they're all going to have the same number of molecules. Okay, so let's go jump to the next slide here. Okay, so just stay with me. All right, okay, so there was a lot of experiments done, it's fine, on this theory of Avogadro. Okay, and how to calculate this. How do we calculate this, right? What are we talking about here? What does this mean, right? And how many numbers of molecules does this have? How do we determine this, right? Now, lucky for you, you don't actually have to know the entire, because it would be as long as this room, how many number of molecules, okay? Luckily, we have sort of a shortened, condensed version of this, all right? So the number of molecules that are in each of these gases, same temp, same pressure, number of molecules. So 1, same number of molecules. And you're gonna be saying it in your sleep, because I do. 6.02 times 10 to the 23rd. 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 Everyone say it with me. 6.02 times 10 to the 23rd. Yes, 6.02 times 10 to the 23rd. Number of molecules. Okay, this is number of molecules. This isn't anything else except for number of molecules. Number of molecules. 6.02 times 10 to the 23rd. Number of molecules. At the same temp and the same pressure, any gas has the same number of molecules, and it is 6.02 times 10 to the 23rd. Number of molecules. All right. And the same pressure. That's right. Okay. What is next? Oh no, she's gonna get fired over there.
She's losing her extra credit point.
Can we stop there?
Stamping.
Oh, she's gonna start stamping.
She's like, who cares about extra credit points?
Okay. All right, we'll stop there. Okay.
Do we have a study fund